All right, here I'm going to go through 9 problems about polynomials. This will be 9 good problems to look over as you are making a final study for the finals here. We'll start with number 1 here. Name the polynomial by degree and number of terms, and then state the end behavior. All right, so degree refers to the number in the exponent. So we have a degree which equals 2, which means it is quadratic. Number of terms. Everything being multiplied gets glued together. This is just one term, which means it is a monomial. When we put those together, it gives us a quadratic monomial. All right, to figure out the end behavior, we need to look at the degree again, but specifically, is it even or is it odd? This one, we have an even degree. This tells us that the end behaviors must match. All right, then we look at our leading coefficient. This is a negative leading coefficient. That tells us that it finishes down. So the end behavior is down, down. They have to match, and it finishes down. The only way to make that work is to make it down, down. Or we could say it falls to the left, and it falls to the right. All right, problem number 2. Find all zeros and state their multiplicity. So here we're going to use the zero product property to state that we've got a bunch of different things here being multiplied. We're going to call those things factors. But if you've got a bunch of things being multiplied, if you can make one of those 0, it'll make the whole thing 0, and you will have found a quote-unquote 0. So x squared equals 0, 3x minus 1 equals 0, x squared plus 5 equals 0. All right, let's solve this. This gives us a 0 at 0, but because of the 2, it gets a multiplicity. So it's 0 mult 2, so it's 2 zeros at the same place. This one here, I got to add 1 to both sides. You got 3x equals 1, divide both sides by 3. I've got x equals 1/3. That's just a multiplicity of 1. That factor is only in there once. And over here, I subtract 5. Got x squared equals -5. Square root. I get x equals plus or minus 5i. Square root of 5i. So when I take the square root of a negative number, that negative jumps out and becomes an I. All right, so far so good. Those both have a multiplicity of 1, the positive 5i and the negative 5i, or square root of 5i. All right, divide. This one we can do synthetic division, so we will. The root is at -8. That's because -8 is the value that would make this 0. So that's what we're going to use when we do synthetic division. So let's grab all the coefficients, 1, 16, 65, and 8. We'll do synthetic division with a -8. We drop down the 1, and then it's just multiply, add. Multiply, add. Multiply, add. Multiply, add. And then these become the coefficients of our new polynomial, n squared plus 8n plus 1. It always, if you divide by a linear equation, you're always going to decrease your degree by 1. So I knew it had to be a squared. And then this, this works out. We get a nice quadratic trinomial. That is what that equals once we simplify. All right. Write a polynomial function in standard form that has the given zeros. So here we got to do the zero product property backwards. So x minus a 0 gives us a factor. So we've got x minus 4, x minus a negative 3i. But the thing is, we can't just have one imaginary 0. We also have to include the factor x plus a negative 3i. This is the conjugate because we flip the middle operator. And the reason we knew we needed to do that was because of conjugate root theorem. So technically, we're missing a word in the setup of this problem. Write a polynomial function in standard form with integer coefficients. Because technically, you don't have to apply conjugate root theorem if you're allowed imaginary or complex coefficients. But we rarely will see that in math. All right, so let's simplify this out, and to get into standard form, we'll need to do some distribution. Now I've got x plus 3i, x minus 3i. These are the two I'm going to distribute first because they're conjugates. I know their middle term is going to cancel out. So first, outside, inside, last, we get x squared minus 3ix plus 3ix. And minus 9i squared. And let's keep this x minus 4 going over here. So these two terms cancel. I squared is equal to negative 1, so negative 9 times a negative 1 becomes a positive 9. Now we've got the expression x minus 4 times x squared plus 9. We'll FOIL this, and I'm just going to do it so that I make sure I get it into standard form right away. First, inside, outside, last. All right, there we go. Standard form, integral coefficients. Excuse me. All right, solve by factoring. First thing you look for in factoring is, do I have a greatest common factor? The coefficients, well, this has got a coefficient of 1, so I can't divide anything out, but they do all have an x. So I can take an x out, put it out here, and everything just got 1 degree more simple. All right, so now if I wanted to go back, I would distribute that x. I'd go right back to this. But factoring is essentially undoing distribution. Now this here with 4 terms equals think factoring by grouping. It's not always going to work. You might have to test rational roots, but if it does work, it saves you a lot of time. So now I've got x. I can pull an x squared out of this, leaving behind an x minus 4. I can pull a negative 2 out of this, leaving behind an x minus 4. 0, and now I rearrange into the different factors. And if you go on Khan Academy, they have a great video about how factoring by grouping works. If you're struggling with this step here, going from here to here to here, I highly recommend that. Check it out. It's one of the things I assigned. So yeah, just look up factoring by grouping and you'll find it. All right, now that we've got this down to binomial factors, we can start using the zero product property and setting them equal to 0. Set that first one equal to 0, we get x equals 0. We've already found an answer. The second binomial factor, we set that equal to 0. Well, we're going to have to solve this. Won't take us too long. We'll add 2 to both sides, get an x squared equals 2. Take a square root. We get x equals plus or minus the square root of 2. And our last one, x minus 4 equals 0. I add 4 to both sides. And we get x equals 4. All right, and there's all of our roots. There's 4 of them. The fundamental theorem of algebra predicts a 4th degree polynomial should have 4 roots. Plus or minus cancels 2. All right, state the number of zeros, the possible number of real and imaginary zeros, and the possible rational roots. So when it says number of zeros, sometimes we'll see this as complex zeros, because complex includes all things rational and irrational and imaginary. So number of zeros equals 4. It's always equal to the degree. There's a kind of a caveat here. It's like if you count imaginary and multiplicities separate. All right. So we know we must have 4. Those 4 complex zeros, they can be either imaginary or real. So let's make possible combinations of imaginary and real. We could have 0 imaginary. That's always an option. Imaginary, I spelled that wrong. It's an A. All right, so if I have 0 imaginary, then I must have 4 real to complete the 4 complex that I know I have. Now, I can't just have 1 imaginary. That does not work because they always come in pairs. My next option is 2 imaginary, which would leave space for 2 real. And then my last option is 4 imaginary, which leaves space for 0 real roots. So sometimes I'll ask if I have a 3rd degree polynomial and I already know I've got these 2 different imaginary roots or something like that. I'll ask if I can fit another root in. Well, let's say it's a 3rd degree. I know 1 imaginary root. Can I fit a different imaginary root in? The answer would be no, because each of them need to bring in their conjugate as a pair, and we would run out of spaces in a 3rd degree, which can only have 3 roots. So yeah, it's a common type of question I'll ask that uses the fundamental theorem of algebra. All right, so for rational roots, we need to assemble our list of P and Q. P is going to be all the factors of that last number. For 15, that's 1, 3, 5, and 15. And for Q, that's just 1 and 2. Now I want to make all of the fractions possible with P over Q. And so I've got 1 over 1, 1 over 2, 3 over 1, 3 over 2, 5 over 1, 5 over 2, 15 over 1, and 15 over 2. And then I want to add a little plus minus at the very front because all of these also have a negative case. All right, let's simplify that down. We've got 1, 1 half, 3, 3 halves, 5, 5 halves, 15, and 15 halves. And they're all plus or minus. All right, moving on. Find all zeros by testing rational roots. All right, so P equals just 1. Q equals 1, 2, or 4, all the factors of 4. Let's make all of our fractions possible. We've got 1 over 1, 1 over 2, 1 over 4. Those can all be either plus or minus. So here's what we're going to do. What I'm going to do is I'm going to start with the coefficients 4, 9, 6, 1, and just start doing synthetic division with these numbers here until I find one that works. Let's start by testing 1. So we got 4, 13, 13, 19, this isn't going to work, 20. So that's a no. Let's see, we got 4, 9, 6, 1. Let's test -1. So drop the 4, get a -4, 5, -5, 1, -1, 0. All right, this is a yes. Let's check for multiplicities by taking that same bottom row, checking it again with -1 to see if -1 has a multiplicity. So 4, 5, 1. Let's check that with -1. I've got 4, -4, 1, -1, 0. This is yes, so we know -1 mult 2, but also we don't really have to keep going because this here gives us the equation 4x plus 1. Set that equal to 0, and we'll get x equals -1/4, which was in our list. And now we found all 3 of this cubic's roots. It just so happens that 2 of them were in the same spot at -1. All right, find all zeros. 1 0 has been given. So if you are given a 0, that is irrational. Technically, 2 zeros have been given because 3 minus 2i must also be a 0 by the conjugate root theorem. So when you know zeros, you also know factors because x minus a root is a factor. So we have 2 factors here. We've got, and I'll write them over here, x minus 3 plus 2i and x minus 3 minus 2i. Let's distribute the negative there. We get x minus 3 minus 2i and x minus 3 plus 2i after I distribute the negative. All right, let's keep distributing these, see what we get. I'll do my first term to all 3, so I get an x squared minus 3x plus 2ix. Middle term to all 3, -3x plus 9 minus 6i. And then the last term, we get a -2ix, positive 6i. And then -2i times a positive 2i is going to be a -4i squared. That's going to become a positive 4 because I squared equals -1. So let's write this out. We got x squared minus 3x. That cancels with that. Minus 3x plus 9. That cancels with that. And that becomes a plus 4. So I know that this is a quadratic factor of my polynomial. After I combine my like terms, I've got x squared minus 6x plus 13. I know that that is a quadratic factor of this quartic up here. If I know it's a factor, then it should divide in evenly, thus simplifying our polynomial and giving us something that we can probably factor. Just using simple factoring. So here I have to do long division because I've got a quadratic. There's no synthetic division for dividing quadratics into other things. I asked myself what multiplies x squared to get an x to the 4th. Well, that's going to be an x squared. I multiply that to everything. That gives me an x to the 4th minus 6x cubed plus 13x squared. I subtract that away. Thus, and here it's important to keep track of your negatives. Easy to mess up. You get negative 20 minus a negative 6. That's going to become negative 14x squared, or x cubed. Here I've written this a little bit wrong. There should be a 4 there. All right. 110 minus 13. That's going to be a 97 x squared, and we'll drop down our next term. The next thing I want to write up top here, what do I have to multiply x squared by to get a negative 14x cubed? Well, that's going to be a minus 14x, and I get a negative 14x cubed, negative 14x cubed. I get a 14 times 6, and 84 positive 84x squared, and I get a negative 182 x. So let's subtract that away. Well, here I'll use a different color. Subtract it away. Our x cubed terms cancel now. 97 minus 84. That's 13x squared. Negative 260 minus a negative or plus 182 gives us a 78 minus 78x. And then we drop down our last term, a 169. So if this worked, then multiplying by 13 should give me all those numbers. I just want to double check that it did work. Negative 6 times 13 is a negative 78. And then 13 times 13 is 169. So it's going to give us this back exactly. And when we subtract it away, we should get a remainder of 0. All right. So we've simplified our polynomial down to this. Let's pull it out. We got an x squared minus 14x plus 13. That is going to be factorable into an x minus 13 and an x minus 1. That way those two numbers multiply to be positive 13 but add to be a negative 14, which gives us the zeros of x equals 13 and x equals 1. This was a 4th degree polynomial, so we found all 4 roots. We got those 2 up there and these 2 down here. All right, problem 9, expand completely. Here we're going to use binomial theorem. I'm going to need the 4th row of Pascal's triangle, so I'll quickly sketch a Pascal's triangle. All right, let's fill it in with our a's and b's now. So we want 1a to the 4th plus 4a to the 3rd b plus 6a squared b squared. Notice I'm counting down with my a's and up with my b's. Plus 4a b to the 3rd plus 1b to the 4th. Let's fill it in with 4y equals a and 1 equals b. So we got 1 times 4y to the 4th plus 4 times 4y to the 3rd times 1 plus 6 times 4y squared times 1 squared plus 4 times 4y times 1 cubed plus 1 times 1 to the 4th. Let's keep simplifying. This is going to become 4 to the 4th y to the 4th plus 4 times 4 to the 3rd y to the 3rd plus 6 times 4 squared times y squared plus 16y plus 1. All right, so notice I had to distribute the exponent. When you've got something being multiplied, then being raised to an exponent, you got to distribute. 4 to the fourth is 256. Y to the fourth plus, this would be 256, y to the fourth again. Y to the third plus 6 times 16, 96, y squared plus 16y plus 1. All right, it's expanded completely. And with that, that was our last problem. I'll end the video here, and good luck studying for the test.